So here, number 3, we have the applied optimization problem. It's similar to a lot of them we did, but it's a little bit different, give you a chance to be just a little bit creative. This is the problem that people who took it while in quarantine got a slightly different problem because I wanted to show the picture, and it's just easier sending those tests electronically, not to use a picture. All right, so we read the problem. For rectangular rose gardens surrounded by walkways of various widths. For the morning class, 3 meters on each of these 3 sides and 1 meter down on the bottom. Okay, the rose garden, this area inside here, needs to have 10 square meters of territory, and our goal is to minimize the combined area, which is in the form of a rectangle. You can see the easiest way to solve this is to let our variables be the dimensions of the inner rectangle. Then we get a really nice formula because we know the area. So let's let x be the width and y be the length. And so we know, I'll write it over here, whatever we do, that x times y has to be 10 because it's the area xy, and we want that to be 10. And now we want to minimize the total area. Well, the total, it's another rectangle. So we'll just call it T here. And how long is it? Well, the morning class, all of these sides were 3. In the afternoon class, they were all 2, so slight difference. The overall size length of the rectangle, the width of it is x plus 6. It's x plus 2 walkways. And the height is y plus 4. That's the function. We need to write it as a function of one variable. So if you multiply that out, we get xy. You want to FOIL it. Plus 4x plus 6y plus 24. So this xy is 10. All right. We have to have 10 units. So I can add the 10 to the 24 and get 34 plus 4x. And then I'm going to solve for y over here. Y is 10 over x. And plug it in. With this thick pencil, I'm using my space up fast. I'm going to plug it in one step here. You can see how it goes. Oh, I made a mistake. Need some space for this thing. So we have 6 times y is 10 over x, so let's write that as 60 over x. And then we have a function of x. It's clear that x can be any positive number, and we could build that rectangle. So we have an open interval. Obviously, x can't be 0, but there's no limit to how big it can be. And so we are going to use method 2. An open interval, that's the key. Again, we don't have a choice. The problem dictates what the right method is. And this one has an open interval. So now we'll take the derivative. I get 4, 0 plus 4 minus 60 over x squared. Set it equal to 0. And solve that. I get x is the square root of 15. I'll let you do the algebra. Now, that's a critical point. A critical point does not guarantee a local extreme value. And if it did, it doesn't guarantee a minimum, the kind we want. So we got to take it one step further. We need to run through either the first derivative test or the second derivative test. That's how we decide at a given critical point what's going on. Well, the second derivative is super easy to get here and analyze. So here's the first derivative over here. Now just take the derivative and I get 120 over x cubed. Right, the derivative of 4 is 0. And then this term is like, this term here is like 60x to the minus 2. So bring that 2 down. It's going to flip the sign because it's negative. It's going to flip the sign back to positive, and I get 120 over x cubed. I can go back to black. And that's positive. So by the second derivative test, see if I can squeeze in my summary here. By the SDT, we have a local min concave up. Well, we had exactly one critical point, and it corresponds to exactly one local min. So by method 2, it's absolute. Perfect. Now, remember the last thing we do is answer the question. So here's the question. Determine dimensions. Should have been spelled right, but that's okay. So I've got the x. All I need is the y. And I'm going to write it up here. I got a little more space. X is the square root of 15. Y is 10 divided by the square root of 15. Right, there's our y right there. And you don't need to simplify those. That's the right answer. So we'll move on to the next problem. Next problem may have been the easiest one on the exam. There was one sort of catch here for the other two classes, but here we have a third degree polynomial in the numerator, right? This third power right there. And if you multiply the bottom out, it's also a third degree polynomial. The limit is at infinity. So polynomial divided by polynomial, the limit is going to be the ratio of the leading coefficients, and that's 3/64. If you cube the bottom out, you're going to have 4x times 4x times 4x. 4 cubed is 64. For the noon and 1 o'clock classes, this was supposed to be the same kind of problem, but it turns out this 3, the cube, went missing. And so you had a kind of weird looking second degree polynomial where you had x terms here and x terms there. You can still solve the problem, and we knew how to do it. Now we have a second degree over a third degree, so that is going to be 0. The limit's at infinity still. So we have a higher degree on the bottom. So this is for noon and 1 o'clock, and this is for 8 o'clock. So over here we have a limit at 0, and the sign of 0 is 0. If we take a close look, like the numerator goes to 0, the bottom goes to 0. And so we don't know what the limit is, but we have permission to do L'Hopital's rule. So we'll take the limit as x goes to 0. Some of you forgot the chain rule, like how could you do such a thing? 2e to the 2x, 5 cosine 5x. And that goes to 2 over 5, which is perfect. It's our answer, 2/5. So the answer is this and that. And for those of you in 12 or 1, might have been, I think there was a 3 instead of a 2, so it's a little bit different, but not too much. All right, number 5. Oh, I forgot to mention, you'll notice that, starting here, these instructions, like one of the remaining problems will not be used in your grade. It'll be the one you scored least on. All right, number 5. So this is an approximating error problem. I was kind of frustrated with how few people drew a graph out. I mean, you don't even have to draw the right graph, but we know this one. It's a hyperbola. The vertical asymptote is at -1. We're safely away from it. So we know the graph is going to do something like this. We want to go from 2 to 10. And I said n equals 4, so let's calculate delta x. It's 10 minus 2 divided by 4. Look at that, a nice integer, and so nice to you. So the breakpoints are going to be, we're going to scoot over 2. We're going to go to 4, and then 6, and then 8. And I said use right-hand endpoints, so there's our 4 rectangles. And our approximation is the height of the first one is the functional value at 4, which is 1/5, right? Plug it in, add 1, times 2, the width. And then the functional value at 6, it just goes up by 2, 1/7 times 2, plus 1/9 times 2, plus 1/11 times 2. And there is our answer. And I did say you do not need to evaluate the expression. So there you have it. I think at noon and 1, I change it n equal to 3, and I change the interval, and I even change the function, but the concept is exactly the same. encourage you to just, on any problem we're trying to solve, it's easier to figure out if we have a picture. So, I mean, even if you didn't know what the function looked like, and we certainly should, it's a hyperbola, but you could draw the region from 2 to 10, and you could put your rectangles in there and then use the function to get the heights of each rectangle. All right, that's page 2.